Hello everyone, my name is Kurpisz. I'm from ETH Zurich, and it's my great honor and pleasure to present our paper entitled Sum of Squares Certification for Symmetric Quadratic Functions and its Connection to Constrained Boolean Hypercube Optimization. The paper was written in collaboration with Potechin from University of Chicago and Elias Wirth from TU Berlin. So today we are interested in functions of the following form. Consider function qk that maps verts of the Boolean hypercube to real numbers of the following form. And this function is parameterized by k that can take values from 1 up to n. And the first question we'd like to ask is, can we write qk as a sum of squares of polynomials, meaning in that way? And actually the answer is no, we can do that. And the reason is trivial, just because sum of squares of polynomials are globally non-negative, and our polynomial qk of x is negative in the interval from k minus 1 to k. So let's modify the question a bit and ask the question, can we write qk as summation of polynomial squared plus a term that will vanish on the verse of the Boolean hypercube? And actually in this case, the answer is yes, we can do that. And here is a sample how to do it for k equal 1. So let's write q1 of x in that form. Let's open the brackets. We get the following three terms. And we'll start with the term in the middle, meaning summation over all I different than j, xi times xj. And this actually can be written in the following way. So we'll get summation of xi xj squared minus some term, a compensating term, that actually will vanish over the Boolean hypercube just because it has these two constraints, these two terms in the middle, and they vanish over the Boolean hypercube. And finally, the summation of xi squared minus summation of xi can be put together in this way, and this term again vanishes of the Boolean hypercube. So just to conclude, we wrote q1 of x as a summation of a monomial squared minus plus some term that vanishes over the Boolean hypercube. So the question is, can we do this for k greater than 1, for example, for k equal 2? And actually, even for k equal 2 is much more difficult. So for the polynomial you can see on the right, it's not that easy anymore. And if we push k up to n over 2 rounded up, we will see that actually the degree of the sum of squares needed to write the function qk in that form goes up to n over 2 rounded down. And in this paper, we'll try to answer the question, what is the sum of squares, what is the degree of the sum of squares representation needed to write our polynomial qk in that form? But before we answer this question, let's maybe motivate a bit why we are interested in representing a polynomial as a sum of squares and why we're interested in this specific function at all. So let's consider polynomial optimization problem, the general polynomial optimization problem. So given the polynomials f and g1 up to gm, we would like to find the minimum of the polynomial f of x subject to polynomial constraints composed of this polynomial gi of x. So we can rewrite it a bit. So consider a calligraphic set G, and this is the set of all these polynomial constraints, and the corresponding set G plus, which is a feasibility set, meaning the subset of Rn composed of all the x's, such that these constraints Gi are non-negative. And then polynomial optimization problem can be written as minimizing polynomial f of x, such that x belongs to the feasibility set. So here is an example. Imagine that the blue curve is a polynomial f of x, and you would like to minimize over the feasibility set composed of the red points. So the minimum is maybe somewhere here for x equal 10. And actually this minimum is equal to the amount of units I can push my function f of x down such that it stays non-negative over this feasibility set, in this case, this red dots. So we get the following formulation, So now we would like to, instead of minimizing f of x, I would like to maximize the real lambda such that f minus lambda stays non-negative over the visibility set, and this kg is nothing else than the cone of polynomials that are non-negative over the set G plus. Of course, we haven't done anything spectacular, so the problem on the right has to be as difficult as the problem on the left. So what we would like to do, we would like to actually approximate this cone kg effectively, meaning we would like to get good approximation, and at the same time, we would like to allow efficient optimization over this cone. The cornerstone result in this direction is the Putner positive Stellenses theorem that states, under some mild conditions the set G plus has to satisfy, that every strictly positive polynomial P of x over the set G plus admits the sum of squares representation of that form. And this is a certificate of non-negativity of the polynomial P of x, just because this S0 and Si are sum of squares polynomials that are globally non-negative, and these polynomials Gi are exactly polynomials defining the feasibility set. The measure of the complexity of this certificate of non-negativity is the maximum degree of the polynomials Si we use in the certificate. And in this case, we get the whole family of relaxations of polynomial optimization problems by restricting this set Kg of non-negative polynomials to polynomials that are non-negative, but that also admit a sum of squares certificate of non-negativity of given degree D. And this actually can be automatized, since this can be solved with the SDP of size roughly n plus d, choose d. When we look at a specific case of optimization of the Boolean hypercube, we have to modify things a bit. And in this case, what we do, we add to our set calligraphic G the set of polynomials that are algebraic description of the verts of the Boolean hypercube. So let's give a look at the function we're interested in, so it's symmetric quadratic function. And in this case, this function attains over the verts of the Boolean hypercube the minimum 0. So lambda in our case is 0. So instead of minimizing qk over the verts of the Boolean hypercube, what we can do, we can try to find this sum of squares polynomials S0, S1 up to Sn, so that qk can be written in that way, so it will admit sum of squares certificate of non-negativity. Good. So now let's motivate this symmetric quadratic function a bit, why we would like to find the sum of squares certificate of non-negativity for exactly this function. And the first motivation is the max cut problem. And actually, when we consider the hardest instance of the max cut problem for the sum of squares hierarchy is exactly given by one of these polynomials qk of that form. And actually, Grigoriev and Laurent proved that the sum of squares degree to certify the size of the maximum cut in an odd clique is equal to the degree needed to certify non-negativity of this polynomial, and in this case is n over 2 rounded up. And this result is actually tied, as proved later on by Favzi, Saunderson, and Parillo. The next motivation is the max CSP problem. In the seminal paper, Lindra, Gavenda, and Steurer proved that SDPs of polynomial size are equivalent in power to those arising from sum of squares proof system of comparable size. And actually, as the key component in the result, they again use the fact that the degree needed to prove non-negativity of this polynomial over the Boolean hypercube. The next motivation comes from query complexity and expectation. Actually, in this problem, the input is a function over the verts of the Boolean hypercube, and the output is a non-negative real number whose expectation exactly equals f of x. And Kaniewski, Lee, and de Wolf proved that the quantum query complexity equals sum of squares degree to prove non-negativity of this function f of x. And for this specific case of Q2, they actually prove that the quantum query complexity of Q2 of X is at least omega square root n, and this directly translates as a lower bound for the degree of the sum of squares certificate to certify non-negativity of this polynomial Q2. And finally, there's also a motivation for approximation theory. An approximation theory would like to approximate a more complicated function with the family of simpler functions. And in this case, one could approximate this qk of x with the sum of squares polynomials. And that was considered with in the paper by Lee, Prakash, de Wolf, and Yen. And actually, they proved that even approximately writing the function qk as with sum of squares within some error epsilon needs a degree at most big O of n and at least omega square root k n times n minus k. So now let's go back to our main question. As I said, we would like to answer the question, what is the degree, the sum of squares degree needed to write our function qk as a sum of squares? And directly by the Lee, Prakash, de Wolf, Yen result, what we get is that actually this degree is at least omega square root k times n minus k, and at most big O of n, and this comes directly from this result. But in this paper, they actually conjectured what should be the proper answer, and they said that the answer, in their opinion, should be theta of n, meaning that they believe that this bound is the correct bound. And actually, our main result is disproving this conjecture, and we prove that the sum of squares degree is at most square root nk times log n factor. So let's give a look at the sketch of the main proof. So as I said, we would like to find sum of squares polynomials S0 and S1 up to Sn, such that qk can be written as sum of squares plus some term that will vanish over the Boolean hypercube. And in that case, what we do say is that qkx minus S0x is a sum of squares modulo the Boolean axioms as it vanishes over the Boolean hypercube. The first observation that we make is that actually it suffices to find a univariate polynomial S0x such that this univariate version of qk of x minus S0 of x will be greater or equal than 0 for all the x's in the interval from 0 to n. And moreover, this S0 should be a sum of squares modulo the Boolean axioms. So let's give a look how we could construct this polynomial. So here in the picture, you can see a polynomial qk of x that is actually negative in the interval k minus 1k. And we would like now to construct a univariate polynomial S0 of x such that this S0 of x will be sum of squares modulo the Boolean axioms, and qkx minus S0x will be greater or equal than 0 in the whole interval from 0 to n. So let's see how we could construct. We will construct this polynomial in two steps. In the first step, we will construct a polynomial S1 of x. The polynomial S1 of x should be the sum of squares modulo the Boolean axiom, so it can be, it doesn't have to be non-negative, but it has to be non-negative modulo the Boolean axioms. It should also have kind of a small degree because that's big O of k. And this polynomial, additionally, you would like this polynomial to be smaller than qk of x in the interval from 0 to k minus 1. Also, here it should be smaller, and up to the point 2k minus 1, it should be below the polynomial qk. And in the interval from 2k minus 1 to n, actually it can grow, but it shouldn't grow too fast. I will write not too fast. okay? And the second polynomial we'll construct is polynomial S2 of x, and this has to be a sum of squares polynomial, so globally non-negative. And from this polynomial, we'd like to have the following. So in the interval from 0 to k minus 1, I would like this polynomial to be below 1. So this polynomial could be maybe something like this. In the interval from k minus 1 to k, it should be greater than 1. And in the interval from k to 2k minus 1, again, it should be at most 1. But in the interval from 2k minus 1 to n, actually this polynomial I would like to be very small. And having these two polynomials, I will construct the polynomial S0 of x as the product of these two polynomials. And now why I claim it's enough? Let's give a look. So from the interval from 0 to k minus 1, the green polynomial, so polynomial S1 of x, is below qk, is smaller or equal than qk. And actually the red one, S2 of x, is smaller or equal than 1. So when I multiply green one and the red one, I'm definitely below qk, below the blue one. In the interval from k minus 1 to k, the green one again is below qk, but now the red one is greater or equal than 1. So when I multiply them, I will again stay under the blue one. In the interval from k to 2k minus 1, it's exactly the same case as from 0 to k. And now in the interval from 2k minus 1 to n, I would like this very small polynomial S2 to compensate the growth of the green polynomial S2 of x. So one just has to be careful there with numbers so that this polynomial, the multiplication of S1 of x and S2 of x will not grow faster than qk of x. So let's give a look how we construct this polynomial S1 a bit more in details. So first what we do, we consider a sum of squares polynomial modulo Boolean axioms of the following form. So this polynomial has k plus 1 roots, and the roots are from in point 0, 1, 2 up to k. So this polynomial looks like this. So it looks like a good candidate for S1 polynomial, but the problem is that here, since the degree is greater than 2, it grows very fast. So this I really don't like in this polynomial. So what we do, we'll consider polynomial g2k minus 1x, and actually this polynomial has 2k roots. It goes up to here, and here it grows very fast. So this is already much better polynomial. However, the picture is a bit misleading since this polynomial here might take a very big values. So we would like to truncate it on the borders and highlight in the middle, and that's why we multiply this with the polynomial with multiple roots at x equals 0 and x equal to k minus 1. And in that sense, we decrease this part a bit down and increase this, highlight this part in the middle. So this is how we roughly construct the polynomial S1 of x. How to construct polynomial S2 of x, and this construction is based on the Chebyshev polynomial. Just to remind, the Chebyshev polynomial is the polynomial defined recursively in this way. So this is 2x times the Chebyshev of degree minus 1 minus Chebyshev of degree minus 2 with these boundary conditions. And actually the polynomial, the Chebyshev polynomial, is the polynomial that for the arguments between minus 1 and 1 always takes value between minus 1 and 1. And moreover, among all the polynomials of degree d that takes values here between minus 1 and 1 is the polynomial that is growing the fastest outside this interval. So now what we would like to do, we'll take this polynomial, we will square it first of all, then we will spread it and shift it, and we will place it in our construction in the following way. So here we would like this polynomial to take the very small values, because it will be multiplied by some very small value, and here outside this it will grow, right? But I wouldn't like this polynomial to grow too fast. I would like this polynomial to grow in a way that here it exactly takes value 1 as needed, and then it might grow even farther. And the last step is just to symmetrize this polynomial among the point k minus 1/2, so that we get the following polynomial. And this is how we construct polynomial S2. And now the degree of this polynomial, as I come directly from the analysis, I don't go deep into the details, but this is exactly how we construct polynomial S2, and then the polynomial S0 is just the multiplication of S1 times polynomial S2. I have a few minutes left, so I would like to tell you something more about some applications of the theorem we proved. And the first one is proving the sum of squares degree to certify an instance of the set cover problem. And in this case, we minimize summation of variables and variables subject to those constraints. We have n constraints. Every constraint is missing one of the variables. And over the Boolean hypercube, the minimum value is 2. And this problem has been studied from different perspectives, from the perspective of different proof systems. And actually, finally, Bienstock and Zuckerberg conjecture that the sum of squares rank of this problem, the sum of squares degree, is at least n/4. And what we managed to prove is we managed to connect the degree of the sum of squares certificate for symmetric quadratic functions with the degree of the sum of squares certificate for the set cover problem in the following sense. So you prove that if there exists a degree d times n sum of squares certificate of non-negativity over the Boolean hypercube for polynomial qk, then there exists a degree d times n sum of squares certificate for the set cover problem, and actually by the result for the symmetric quadratic functions for k equal 2, we know that here we have actually instead of d times n, we have square root n. So the total degree is upper bounded by the square root n log n, and this again refutes Bienstock-Zuckerberg conjecture. And the last application I would like to tell you is an instance of the min knapsack problem. So we minimize again summation of x is subject to this single constraint, and for p equal 2, it was heavily studied again from the perspective of different proof systems. And finally, there was a question raised by Laurent: what is the sum of squares degree for the MK problem? And we managed to apply the machinery for the symmetric quadratic functions to prove that the maximum degree needed to certify this problem is square root or big O of square root n, and this actually is a tight result closing the gap for this problem. So that's all. Thank you so much.